Imagine you're lying flat in the glass nose cone at the very front of a B-17 bomber. It is minus 40 degrees Celsius. The aircraft is shaking. 4 roaring engines, flak bursts going off around you, the whole airframe lurching through smoke. You're at 20,000 feet over Germany. You can't feel your hands. And your one job, the job the entire mission depends on, is to drop a bomb accurately onto a target the size of a factory from 4 miles up. Before guided missiles existed, this is how it was done. Not by instinct, not by eyesight alone. By a mechanical computer so precise its designers claimed it could hit a pickle barrel from 20,000 feet. It almost never did. And the reason why is one of the most fascinating engineering stories of the Second World War. Carl Norden was a Dutch engineer working in America who believed that bombing was fundamentally a math problem. If you knew your altitude, your airspeed, the wind, and the weight of your bomb, a machine could calculate the exact moment to release it. Not a human guess, a mechanical certainty. He spent over a decade building that machine. The Army Air Forces spent $1.5 billion producing it. Every bombardier who flew over Europe swore an oath to protect it with his life. Some carried a pistol specifically to destroy it if the aircraft went down over enemy territory. The device was called the Norden bomb sight. And in 1931, on a Navy test range, it did something that shocked every officer watching. The Norden came in 2 pieces. A sight head with a rotating prism and telescope sat at the bombardier's position in the nose. Below it, bolted to the airframe, was a stabilizer unit housing 2 high-speed gyroscopes. Those gyroscopes spun fast enough to hold a fixed reference plane even as the aircraft rolled and pitched around them. The faster a gyroscope spins, the more it resists being tilted. So Norden used that resistance to create an artificial horizon inside the bomb sight. A stable reference point the optics could anchor to, regardless of what the aircraft was doing around it. The mechanical computer, and it genuinely was a computer, just built from metal rather than silicon, used rotating discs and carefully calculated gear ratios to translate the bombardier's inputs into a continuously updating aim point. As the aircraft moved forward over the ground, the sight automatically drove the telescope angle downward to keep the target centered. The rotating prism compensated for the apparent motion of the ground below, holding the target stationary and the crosshairs even at speed. Norden went further still. The bomb sight connected directly to the aircraft's autopilot through a system called the Automatic Flight Control Equipment. Once the bombardier acquired the target and entered his parameters, the bomb sight could actually steer the aircraft through the final minutes of the bomb run. The bombardier was no longer just operating a targeting instrument. He was, through that instrument, flying the aircraft. In the 1931 Navy trials, 50% of bombs dropped during testing landed directly on the target, making the older Mark 11 sight, which achieved 20%, look primitive. Lieutenant Frederick Entwistle called it revolutionary after that demonstration, and it is difficult to argue with him. Nothing in military aviation had produced results like that before. On a clear day in 1931, over a stationary target with no one shooting back, that promise held up completely. What the test range could not replicate was everything else. Before the bomb run started, the bombardier had to enter a precise set of numbers into the device. True airspeed, altitude above the target, wind speed and direction, the ballistic profile of the specific bomb on the racks. Feed the machine correct numbers and it calculates a correct release point. Feed it numbers that are slightly off and it calculates the correct answer to the wrong question. With complete mechanical confidence. Wind was the worst variable of all. At bombing altitude, between 20,000 and 25,000 feet, the wind rarely matched what the weather officer had reported at the morning briefing. It shifted direction and changed speed across the length of a bomb run. There was no instrument that told the bombardier what it was actually doing at that moment. So he measured it by watching the target drift in the telescope and making manual corrections in real time, while everything else was also happening at once. Doing that on a clear day in a stable aircraft was demanding enough. Doing it in a B-17 lurching through flak bursts at minus 40 degrees Celsius inside the nose, breathing through an oxygen mask that fogged the eyepiece. That was a different problem entirely. The synchronous tracking method required a straight, level approach of several minutes. Anti-aircraft fire forced aircraft into evasive patterns right up until the final approach. If a gyro tumbled from the vibration and shock of a nearby burst, the bombardier had to relevel the entire stabilization platform. That process could take up to 8 minutes. The bomb run was over. The DC motors inside the device shed fine carbon dust as they wore, settling into the bearings and gear meshes. The lubricating oils thickened significantly in the cold, unheated nose at altitude, slowing the gear train and affecting the timing of the automatic release mechanism. The Army Air Forces eventually had to purchase electrically heated blankets just to wrap around the bomb sites in flight, to keep the oil fluid enough for the mechanism to run. Each of these variables, the wind estimate, the vibration, the thickened oil, the abbreviated approach, introduced a small angular error into the release calculation. A single degree of error in release angle at 20,000 feet moves the impact point by roughly 350 feet on the ground. Stack 3 or 4 of those errors together and a 1,200-foot miss is not a surprise. That is 4 city blocks. The machine was doing exactly what it was built to do. The inputs it was receiving were simply not the inputs it needed. In 1943, the 8th Air Force was flying bomber sorties over Europe day after day. The men in those glass nose cones were doing everything right. By the book, by the training, by the machine. The machine just couldn't account for reality. If that's the kind of story that makes you stop and think, how did that actually work and why did it fail? That's exactly what Machine Matter is about. Subscribe so you don't miss what's next. The Army Air Forces trained bombardiers for up to 18 weeks. 18 weeks to master a device with over 2,000 parts, at altitudes where the outside air would kill an unprotected person in minutes. The training was serious. It was also a controlled fiction. Calm weather, flat terrain, stationary targets, nobody shooting back. The bombardier's station in a B-17 was a plexiglass nose cone at the very front of the aircraft. Exposed, cold, and directly in the path of anything coming from ahead. The oxygen mask required at altitude was uncomfortable for extended periods and occasionally failed. The interphone connecting the bombardier to the pilot was unreliable in the aircraft's own electromagnetic interference, so coordination during the most critical minutes often depended on hand signals or nothing at all. A mission over a heavily defended German target could run 8 to 10 hours. By the time the bomb run came, hands that had been still and warm during training were stiff, fatigued, and working through heavy gloves. The fine motor control needed to make precise adjustments to the tracking knobs had degraded significantly. No additional weeks of instruction could change the physics of a shaking airframe over Germany. By mid-war, the standard practice was for an entire formation to release when the lead bombardier released. Curtis LeMay's combat box formations operated this way. Only the lead aircraft actively working the Norden to calculate the drop point. This removed the worst individual performers from the equation and lifted the formation's average accuracy. But it also meant that whatever error the lead bombardier made, or whatever mechanical problem affected the lead aircraft's sight, was replicated across every aircraft in the box simultaneously. The device had gone from individual precision instrument to formation-wide variable. The post-war surveys put hard numbers to what combat crews already knew. In 1943, the 8th Air Force was achieving circular error probabilities around 1,200 feet. By 1945, that had improved to roughly 900 feet, with about 60% of bombs falling within 1,000 feet of the target. But most of that improvement came from LeMay's formation discipline, not from the Norden getting better. The pickle barrel story, it turns out, was largely Carl Norden's own company promoting its product, including an actual demonstration dropping a wooden bomb into a pickle barrel at Madison Square Garden in 1943. Public morale and contract security, not operational reality. And yet nothing Norden built disappeared. The gyro-stabilized platform, the autopilot link, the principle of coupling a targeting solution directly to flight controls. All of it fed into inertial navigation, automated flight control, and eventually the precision-guided munitions that finally delivered what that 1931 test range had seemed to promise. The pickle-barrel accuracy Norden claimed in 1931, guided missiles achieved it 40 years later. The machine was not wrong. It was just 50 years ahead of the materials and conditions it needed to actually work. The Norden didn't fail because the engineering was bad. It failed because reality is harder than a test range. That gap between what a machine promises and what it actually delivers is what this channel keeps coming back to.